Today we're going to learn about combinations, and an important idea is that combinations are directly related to permutations that we did back in section S8.6. And a good example to show you how they're related is this problem here. If you've got 5 letters, A, B, C, D, and E, and you're trying to pick 3 of them, there are really 2 basically different ways you could do it. You could say pick 3 of them where the order matters, and in that case, if you're doing order matters, then you're doing a permutation. But if you do them where order doesn't matter, then that's a combination. And the important idea is that one combination, for example, A, B, C, can be broken down into multiple different permutations. For A, B, C, you could have ABC, ACB, and so on. There are 6 different ways that those 3 letters could be put in a specific order. If you don't care about the order, it's just ABC. But if the order matters, then there's 6 different possibilities. And the same thing would be true for any particular 3 choice of letters. I mean, it doesn't really matter if it's ABD instead of ABC. There are still 6 possibilities. So what this means is that when you're comparing the permutations of 5 things where you pick 3, and you're comparing it to the combinations of 5 things where you pick 3, there's a ratio between these 2 numbers. And the ratio is pretty simple, that the permutations, there are 6 times as many of them as there are combinations. So this is an important ratio. Of course, a very natural question is the ratio always 6 to 1? And the answer is definitely not. For example, imagine if you picked 4 letters and you were trying to compare P54 versus something times C54. Now the question is, for any particular arrangement of letters, if you've got A, B, C, D, how many different ways can you rearrange these? So you could try to list them all out, but that's probably not a good idea. You got A, B, C, D, and then A, B, D, C, and then you've got A, C, B, D, and you've got A, C, D, B, and then you've got, and it's going to be a really long list. So we need something a little bit more efficient so that we can figure out what number is going to go here. And this basically turns out to be its own little baby permutation question. The question here is, how many ways can I rearrange 4 letters? And certainly order matters, right? Because that's kind of the whole point. How many ways can we order 4 letters? And the answer to that is going to be that you've got 4 choices for the first letter, and after you've picked the first letter, then you've got 3 choices for the next letter after that, and then there's 2 choices for the letter after that, and then whatever's left is the 4th letter. In other words, it's 4 factorial. So the relationship between P54 and C54 is a relationship, a ratio of 4 factorial to 1. And you can probably already guess that whatever this number is, that's going to be the factorial that goes in the middle. And you're right. That is exactly the principle to relate, in general, permutations versus combinations. The number of items that you're picking, that factorial is the ratio between how many permutations you get and how many combinations you get. Notice, you're always going to get more permutations and fewer combinations. Now, the problem with this little ratio here is that we already have a formula for permutations. What we need is a formula for combinations. That's the new thing. So what we need to do here is we need to take this r and we need to move it over to the left side of the equation. We need to take it and divide over to the other side in order to make a formula for combinations. And that gives us this. Combinations are permutations divided by r factorial. And if you mix that formula with the formula we had for permutations from before, remember, PNR, the formula was n factorial over n minus r factorial. If you mix those together, you get this combinations formula that doesn't necessarily have to refer to permutations. To be fair, sometimes it's actually easier to do permutations first, because maybe r is a relatively small number or something, and trying to do it as one giant bunch of factorials might actually be harder. So it's a good idea to remember both of these formulas. They can both be useful. So let's do some examples where we use these formulas, just to see how these things fit together. So, first of all, let's talk about a pet peeve of mine. Let's talk about combination locks. So a combination lock has numbers on the front of it. And if you've got a pretty good one, it might have, say, 50 numbers on the face of the lock. And in order to open the lock, typically it requires 3 numbers, but maybe you've got a fancier one that takes more. But let's just say it's 3 numbers. So if you've got 50 numbers on the face of the clock, and you've got 3 numbers you have to pick in order to open the lock, let's try to imagine how long it would take a lock-picking robot to go through each possible combination. Because this is something I sometimes see in, occasionally like science fiction movies where this robot sort of latches onto the dial and goes, spin, 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 and it tries to go through all the various combinations very rapidly. And they make it seem like this is going to happen real quick, like we just have to sit here for half an hour and the thing will be open. But let's actually work through the math here and watch what happens. So the first question you need to ask on any combination permutation word problem, the very first question is, does order matter? And the reason you have to ask that question first is because, depending on the answer, you might be doing a permutation, you might be doing a combination. So in this case, I think it's pretty much common sense that the answer is 100% for sure yes. If you put the numbers into a lock and you don't put them in the right order, the lock is not going to open. Order definitely matters. Well, wait a sec. If order matters, what we're doing here is a permutation. Permutations are the ones where order matters. In other words, when we call these things a combination lock, that is the wrong name. We should be calling these things permutation locks. But every time I call like the lock on my locker in the gym, I call it a permutation lock, people look at me like I'm crazy. So maybe I'm the weirdo and maybe nobody's going to change. But really, it does bother me a little bit because you don't do combinations to figure out combination locks. You do permutations to do combination locks. So, mild frustration on my part, but it's not the end of the world. Okay, so we've identified that this is a permutation problem. We have 50 numbers that we're picking from, and we're going to pick 3 of them. And one slight little twist is that in real combination locks, I don't actually know whether you can have a number repeated. Like, can your combination be 5, 5, 5? Or do the numbers have to be 3 different numbers? I'm assuming that because of the way the mechanics work inside the actual tumblers of the combination lock, that you can't get the same number twice, but I could be really wrong about that. Assuming that you don't repeat numbers, then it's definitely a permutation question. And since r, in this case, is only 3, it's probably easiest to do the permutation here by simply multiplying the first 3 numbers of 50 factorial, instead of trying to get out the whole 50 factorial over 47 factorial nonsense. That's probably not necessary here. So you grab your calculator, you go 50 times 49 times 48, and you find out that there are 117,600 different possible combinations, or really permutations, on the lock. Now this particular lock-picking robot takes 2 seconds to attempt each combination. So now we got to multiply by 2. So 117,600 times 2, we've got 235,200 seconds. How long is that? Well, I don't really know, so I'm going to divide by 60 to turn it into minutes. So let's see, divided by 60, we're down to 3,920 minutes. Well, that's still a long time. Let's divide by 60 again and get down to hours. So that's going to be 65 and a third, 0.3 bar, hours. So if you ever see some sort of, lock-picking robot's going to go through every combination on a combination lock, and this is a normal combination lock. This has just 50 numbers like you would on a bicycle lock. It's going to be there for more than a day. It's going to be multiple days waiting for this thing to go through every possible combination. So when you see something like that, once you have some intuition about numbers, you can realize that's not realistic. That's not going to make sense. Now, one other example. This one is based on an ad that I saw a few years ago where some pizza company said that they had thousands or millions or some ridiculously large number of different pizzas that you could order from them. So let's actually figure out in a fairly realistic situation how many different pizzas are actually a possibility. So in a typical pizza, you've usually got like 3 sizes, like small, medium, and large. We'll throw that into the mix here at the end. The other thing is that you pick toppings from a list. And some lists are longer and some lists are shorter, but it would be fairly reasonable to say that there are 10 possibilities and you're picking up to 5 toppings. Your first question should always be, does order matter? So if you pick, say, pepperoni and green peppers and olives and something else and something else. If you pick 5 toppings to put on your pizza, can you imagine somebody who actually wanted you to put the pepperonis first, then put the olives on top of that, and then put the green peppers over that? Even if somebody tried to order like that, I know that the people who are actually cooking it are going to nod their head and say yes, yes, and then just do whatever the hell they do. Because nobody really cares what order you put things on a pizza. So here, the answer is no. That means we are doing C, 10, 5. And based on the formula we just learned, that's going to be 10 factorial. There's going to be R is 5. So you're going to have 5 factorial. And over here you're going to have 10 minus 5, n minus r factorial, which is also 5 factorial. So here you're going to have 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And I know you're looking at this thinking, why are you actually writing out these factorials? That's crazy. Wait till you see. It's actually kind of clever. There's some neat stuff that happens if you actually write out the factorials every once in a while. Now, I wouldn't do this if it was like 50 factorial. That would be really kind of not sensible. But here, notice, you get a lot of cancellation. And in fact, you've got even more cancellation than that. 5 times 2 is 10. So these parts are all going to cancel out. And 4 will go into 8 2 times. And 3 will go into 6 2 times. So if you actually take a second to try to write out the combinations or permutations that you're trying to work out, sometimes they're really pretty simple. Like here, I just have to go 9 times 2 times 7 times 2, and I get 252. There is one little twist here that makes this a slightly more complicated problem, and it has to do with this. It says up to 5 toppings, which means they could also do 4 toppings. They could also do 3 toppings. They could also do 2 toppings. They could also do 1 topping. And of course, they could just pick a cheese pizza with no toppings at all. That's entirely a possibility. So we don't just have 252 possibilities. we've got to take 252, and we have to add all these other possibilities as well. Some of these are pretty easy, though. Like, if you just have a cheese pizza, there's one way to do that. If you put no toppings on it, you have one type of pizza you're making. If you're picking one topping out of 10, we don't need any formulas to figure that out. There are 10 ways to do that. Now for C10.2, I'm going to do P10.2, and I'm going to divide by 2 factorial, the alternate version of our formula for combinations. And the reason I'm going to do this is P10.2 is just 10 times 9, and 2 factorial is just 2 times 1, and that's going to be 5 times 9 is 45. So some of these formulas are easier in one version, or they're easier in another version. So here, for this one, same idea. I'm going to do P10.3 over 3 factorial, and that's going to give us 1098 over 321, and we get some cancellation here, and we get 120. Now C10.4, that's kind of a borderline case. I'm not sure which one would be better. I think I'll just do it this way, 10987 over 4321, and see what kinds of canceling I can get in there. And there's some pretty nice canceling. The 8 will cancel with the 4 times 2, and the 9 times 3 will cancel with the 3, so I'll get 21 times 10 is 210. So yeah, that worked out pretty good. Then we add up all of these. So the total number of different pizzas they can make is 252 plus 210 plus 120 plus 45 plus 10 plus 1 is 638 different pizzas. Now, there's a little bit more than that because there are, frankly, 3 different sizes. So there are 638 small pizzas you could make. There are 638 medium pizzas you could make. And there are 638 large pizzas you could make, so you could multiply this by 3. Then that would be a fair conclusion. If they said that there are nearly 2,000 different pizzas you can make, that's a fair claim. That would be a true statement. But if they were to say that there are millions of different pizzas that you could make, based on this situation, millions, I'm sorry, that is not a fair statement. That's deceptive advertising. So, notice how both of these questions have as their first question, does order matter? And once you've figured out whether order matters, that completely controls the rest of the problem. It controls whether you're doing permutations or whether you're doing combinations. And from then on, it's just a matter of figuring out N and R and plugging into formulas.